recently. Here on this desktops, I was just looking for this Matlab symbol and clicking on it, and then it pops up. So the most important thing that those who are remotely and those who are watching the recordings do have an access to it, because it's a primary tool, primary instrument. And you can slowly start, not waiting for the next meeting, maybe do it slowly but surely, finishing earlier today. So did you get any experience in Linux before? Did you install like Linux on your personal computer? It's not a problem. I'm just curious. It's not necessary for this course. But a lot of advanced computing is done in a Linux style, where one types commands instead of clicking on the mouse. So and Matlab is one of those interpreters. So you can just click like demo or help and explore what is going on. And like when we all were little kids, one of the way to learn something is to break it on pieces, right? So just try to click on all possible buttons and check what is happening. Like, if you type help, it answers something. If you type demo, type something. By the way, I remember from the previous year, I remember it was critical to show the better font. And the visual appearance. Oh, I figure it out later. How to change configuration. So let's try to do simple things. So Matlab can be used as a calculator. If you type 1 + 1, it will answer. So, and anything you may need, it does. So you just do some arithmetic and it will work, right? So just try some examples, and we are looking forward to the okay, now you'll hear Spencer if he speaks. I just unmuted the sound. So the next presentation in about 3 weeks will be on the skills, and we need to get comfortable with using Matlab. So let's type something like SQRT of 4. So let me know what are you getting. Yeah, very good. What are you getting if you type SQRT of 1? And you know, if you push arrow up, it will bring up the stuff that you just typed before, so to save time and effort. So now try to make square root of -1 and tell what happens. Okay. Now let's do maybe some variable like I equals this stuff. And after that, if I type who, it tells, okay, we do have new variable ii. Now let's type ii times ii. What do you get? Excellent, excellent. So you see we can operate with complex numbers. Good. What else? Let's do x equals 0, open rectangular bracket, and 0 space 1 space 2 space 3 space 4 space 5, whatever, close rectangular bracket. So one can, does it work? And so now if you type who, it shows there is one more variable, this x capital. And it looks like an array, right? A list of numbers. What if you type x prime? Just type x prime and tell what are you getting? No. Uppercase x, same as you did before. So instead of row, it did a column. Now let's try to do this x prime in the brackets and put one more prime. What do you get? Huh? Yeah, yeah. So you can vector column and vector row can be like transposed. Right? What else? Let's type plot x uppercase. I don't think it is very intellectual, but it shows. And I'm going just to check with Spencer. Please type or say if I have forgotten to ask if you have an access to Matlab. So, okay, I'm so happy. And can you follow little exercises that we are doing? Super, super. Okay. I was worrying a little bit. You need to make sure that everyone has it. Okay. So we did a plot. So there are like 6 records, and they start from on the x and on the y. There are like the values goes from 0 to 5. What if I do x comma apostrophe 0 apostrophe? What do you get? Just describe by words. Otherwise, okay. So it's just graphical representation of data points, right? Or one can do both circles and lines if you need to represent them, right? Now, what if we type instead of x to the power 2? What do you get? You can tell it even without doing. You know which function will be if you do x to the power 2. Okay, try to put period in front of the power sign. Okay. What you can do, x comma, just add x comma in front of this so that we have x and y in the. So now our x-axis goes from 0 to 5 and y goes as a x squared. And one can add like their labels. Okay, what else can we do? And what one can do instead of plot, one can do bar. Not like bar with drinks, but I think the remove this. If you make a histogram for some data, it's maybe more important. So if we are thinking about utilizing this tool in for anything in the course or for just as a scientific calculator, what if you need to plot functions? What is what you do not like? Oh, polar coordinates we can do later, but right now we did in our 5 minutes exploration, we did only discrete values which are very sparse. And if I need to make 1,000 points, I'm not sure that I do have enough steam to put them like 0.1, 0.2, 0.3, 0.5, right? So there should be some smart way to set up the let's call it xx equals 0 with step 0.1 up to, let's say, 10. Will it work? Yeah. And if I'm bored to watch the screen when it is garbage by result, I put semicolon at the end. And then it just defines the variable and doesn't explores my patience with viewing the garbage. Now, if I do plot xx, it should be going more continuously. So that these circles overlap with each other. And if I practice a point simplifier 2, then the function will be presented a little bit more continuous. Right? Of course, we do not need any computers to draw parabolas. It's a little silly. But one can plot different functions, like maybe sine of this argument. So a little better, right? So there are two directions that we need to go. One direction is further into description of functions and maybe derivatives and integration and complex numbers. And another direction is matrices. And they both are needed. We cannot decline one and give preference to another. Just the Matlab doesn't mean mathematics lab. It is matrix lab. So it is primary goal is to work with matrices. And as we discussed today in the class, a lot of equations look like eigenvalue problem, like operator acts on a known function. And right now it's too early. I'm just giving a little heads up. A lot of functions can be recorded as vectors. A lot of operators can be recorded as matrices. And again, in narrow sense, physical chemistry and quantum theory is just finding eigenvalues of a matrix. Therefore, we need matrix abortive. Make sense? Okay. And if you do not get tired, probably you can get to matrix even today. But I'll continue a little bit on functions. So, what if we type, okay, let's recall our short vector x. And now type diff of the x. What are you going to get? Okay, and how do you interpret it? So number of ones is less. Right? So if I type like maybe y equals diff(x), then I type size x, it's like matrix of 1 by 6, vector with 6 elements. If I type size y, it will be 5. So can you guess how this diff works? What does it mean? A little less, a little more prosaic. So it's a difference. So you last minus second last, 1. Second last minus third last, 1. 3 minus 2, 1. 2 minus 1, 1. And number of differences is less than total number of records. If we take the x squared and then apply diff of this stuff, what are you going to get? So 25 minus 16, 9. 16 minus 9, 7. 9 minus 4, 5. 4 minus 1, 3. 1 minus 0, 1. So what if I plot this thing? Plot differences of the quadratic function. Maybe with circles and lines. So any observation? So the quadratic function ramps up, it goes quicker and quicker. The curvature changes, right? As we depart from the origin. Here, the difference grows linearly, so the slope doesn't change. Now let's compare to so dx of x squared versus x, right? Grows linearly. And right now our time step finding difference is very coarse, very rough, but generally we can be much more gentle and just define x-axis with like high density, a lot of points, right? as we did with this 2 capital X's. And just right now we are doing the silly exercises with quadratic function, but we can try something more interesting. If I really want to convert this difference into definition of derivative, what should I do? So I should divide this difference, divide by dx. And dx in our situation for this exercise was 1, right? So in the denominator, we just, nothing is changed. So difference of the function in the nearest neighbors, in the nominator, difference of the steps along argument in the denominator. Now, if we are going to practice this double x, we need to check x. Maybe look on the very few first elements. So they are offset by 0.1. So we can set dx equals xx 2 minus x of 1. Or I can manually set it to be 0.1. And now, if I practice this stuff, it will be again this linear function which is derivative of quadratic, but it defined much more, how to say, gentle. What is the derivative of sine function? Let's check. So cosine starts with 1. Oh, and we can starts with 1 in 0, right? It goes down and go up. So we just implement the definition of derivative. So difference of the nearest neighbors divided by increment of the argument, right? What's the derivative of cosine? Let's check. It starts from 0, goes down, reaches value 1, and then starts oscillating further. Make sense? Okay. Let's set up. We are going to do something more with complex numbers and functions, and I will just check with Spencer. Do you have any questions, or we are good to continue further? Any comments 1? Any comments 2? Any comments 3? So very good, very good. Thank you for confirming. Now let's play exp I times x. And I do not want to watch garbage, I just do it. So guess what is hidden in the variable z? So it is each element of the z vector has both real and imaginary component, right? Because we practice this imaginary exponential. And maybe it's better to do finer resolution. Then it will be much more elements. Now, how can we imagine what is the complex function? So we can plot 3 x. Oh, let's just try to put z in. No, it doesn't want. Okay, x real z imaginary z. Okay, it doesn't. There is no error message. So here is the object that you are discussing today in the class. Did you get anything similar? What approach? I'm in the glove, so I'll type with your permission. Yep. So, visual things are much more pleasant for humans than boring and abstract. So, let's find this rotate 3D pictogram. Depending on which version of Matlab you are using, it can be implemented differently, but I think here is this one. I just check this rotate 3D, click on the image and just play with it a little. So it looks like a little piece of coil, right? So usually for regular real functions, we have one component. For complex, we have two components. And if it is this famous exponential function, it looks like real and imaginary parts are connected. And they continuously define this coil. So when we are writing this exponential to imaginary power, it means we imagine this coil. One can look on the real and imaginary parts separately. Just remove this 3, just plot x. So that we know where is what, dashes. So real will be solid and imaginary will be dashes. So you see that real behaves like a cosine, right? You see it? And imaginary behaves like a sine. Does it remind you something? What's the name of the person who designed this equation? Euler? So this one is real, and everything after this imaginary unit is imaginary. So you see sine, cosine. Yes, if x is cosine and y is sine, then together it makes this helix. One can also do parametric plot. So if you do two-dimensional plot, we remove the argument and plot only real and imaginary. What are you getting? Or you can guess what are you getting before making an experiment. What do you get? So if the x projection, y projection changes in a correlated way, like as sine and cosine, it is very close to polar coordinates, and it defines a circle with radius 1. And then it deals with if you do square cosine phi square plus sine phi square equals what? It is the only thing that one can memorize from high school trigonometry. You see it on the picture. From 0, radius, yes. Yes, but here the radius r equals 1. Okay, very good. So I hated trigonometry in high school and keep this feeling for the whole life. So I'm with you.
Thanks for the optimism.
So what can we add to the functions? Integration. So their integrals can be indefinite and definite. And for this stuff, there is no simple command for indefinite integrals. You know, it's not symbolic integration. We are doing only numerical things, but there is a definite integration when you just add together area under the curve, right? So one can, let's go back to our small thing and just type sum x. Can you guess what we will get? 5 plus 4 plus, or one can do it quicker. 5 plus 0, 5, 4 plus 1, 5, 3 plus 2, 5, 15. Right? Correct? So just adding together. And if we make summation multiplied by dx, here it will be again 15, but it will be approximate numerical integration. And we can, it doesn't need to be linear. We can integrate this quadratic function, and we can try to do it for more finer definition. Now our x ranges are different, so it will be incompatible numbers. It would be more pedagogical to see, but this is a numerical integration of the square function, where we can integrate the this trigonometric sines and cosine. And for trigonometric functions, we are not going to get very big numbers, because they are they're going to oscillate. It adds together pluses and minuses, and it stays within the range. We are progressing 4 times quicker than last year. Maybe 2 dedicated ones, and 1 dedicated online. Let's quickly go to matrices and finish early today. So what if I have variable a? No, I don't. But I can define it as 1, 2, then hitting enter and continue 3, 4, then closing the rectangular bracket. And then how would you define this object A? What is A? Yes. So, are you taking linear algebra? You were taking, or you will take it? I'm with you. I hate it a lot, and I got C in and kept. Huh?
A lot of good information coming out of this class. Trigonometry stage if you put everything in one place together. I didn't mind I had a really good capacity.
A lot of senior friends, when I was I need, maybe by mistake, but I took linear algebra as in freshman times, and I hated it so much. I thought it is most complicated, but a lot of senior friends were telling me like it is one of the easiest for the advanced course. And later on, yes, I kind of agree.
It's hard to me because I've taken calc before. So my doing calculus.
It's just too high concentration of efforts, and you are the hero if you can survive. So what do we do with matrices? Okay, yeah, let's multiply. Let's put like C equals 5 and 6. So C is a column vector. And now I'm going to multiply matrix A by vector C. And just before hitting enter, maybe I should practice what it will be. So 1, 2, 3, 4 multiplied by 5, 6. What should we get? 5 plus 12. And here 3 times 5, 15 plus 24. So it will be 17 and 39. Okay, let's check. Yes. Yeah, let's use it for homeworks in linear algebra.
Yes, sir.
What if we like C apostrophe will be a row vector? What if we multiply A times C prime? What do you get? I bet an error, right? So because we have a rule for row by column, but not row by row. Can we multiply matrix by vector from other side? C prime times A. So 5, 6. 1, 2, 3, 4. We can practice row by column, right? Row by column. So 5 plus 18, row by column 10 plus 24. So it will be 23 and 34. And it should be also not the column, but row. Yes, 23 and 34. Yes. So row by matrix will be row again. Yeah, numbers match. Okay. What else do we do with matrices? Who designed matrices and what was their main goal in the early time, in the time when people were shooting ballistas and early cannons? and just making debit and credit balances in early banks in Italy, like 400 or 500 years ago. No. I can eraser and so sometimes there are, how to say, coupled, combined system of linear equations. Like if you, this equation will be a line, second equation will be a line. And if you solve them together, it will be intersection of lines, just one point. And one can expand it into a multi-dimensional case, like 3 dimensions, 4 dimensions, 100 dimensions. So the question is how to find x and y that would match this equation. Did you get to this point in vanilla algebra? Okay, so what should we do? So we have this 1, 2, 3, 4 is our matrix A, multiply by unknown equals like x equals the known, let's say, let's call it y or b, right? So how would we call, how would we write down the answer? What if we multiply, if you find such matrix A minus 1, that by multiplying by matrix A, it will give 1. And then if we multiply left and right parts of this equation by such A minus 1, A minus 1, A times vector x equals A minus 1, B. So this cancels and we get answer x equals A minus 1, B. So we just need to find inverse matrix, such matrix that will be inverted in respect to this one. So I and V for inverted matrix. We see it's some numbers here. And if you multiply inverted A by A, we get a matrix which will be 1 in a sense of like unitary matrix, right? So if we set up V equals 1 and 2, then we set inverted A times B. So we have 0 and 0.5. Code, and you're following me, right? And now let's check if we type A times C, we should get again this B. Yes, we do. Or A times C minus B should give the column vector complete field of zeros. So the historic reason for matrices and initial like humans were designed matrices to solve coupled linear equations, algebraic equations. Well, of course, we can do old-fashioned, like add and subtract, find linear combination, but when we get to larger and larger things, it gets more and more effort. And without computers, it doesn't matter what you do, but with computers, of course, it is much easier to do this inversion. Now, what is discriminant or determinant? Come on. You took linear algebra? Determinant of a matrix. No. So I feel myself a hero, like telling important information. I'm grateful to this opportunity to to tell this historic aspect. So this equation, solving of linear equations, can be an inverting of a matrix is possible, not always. It's possible only in limited circumstances. And before, if suppose that we need evil bankers that need to just make balances for income and debts, and these equations are done for this aspect. Time is money. We cannot waste time and do operations if we do not have guarantee that they will be successful. So before one is trying to solve equation and invert the matrix, one may make a quick check if it is a good matrix or bad matrix. So the check is so-called determinant, like determine if it is a good matrix. And if it is a good matrix, determinant is different from 0. If it is a bad matrix, then determinant is 0. Did you hear of it? Okay. So if you play with determinant of this 1, 2, 3, 4, what would it be? Diagonal minus counter diagonal. So 1 times 4 minus 2 times 3. So will be minus 1, right? Correct me if I like minus 2. Yeah, thank you. Now you observe that there is no wonder that I got C in linear algebra at my time. So, but it differs from 0, which means we are allowed to try solving this linear algebraic equation. If it would be 0, then it will be no solution. And this is called determinant. So let's just try typing. Right? Okay. So, and what else are we missing with matrices? I think we are doing a month of labs in 1 hour. What else can we do with matrices and vectors? You've mentioned it today. Yes, and before, more simple scalar products. Like if you practice row by column, not for the matrices, but for the vectors, like we have C, and we have B. Okay, let's do B prime, which is row, times the CC, which is column. So this is 1, 2. So we practice again row by column, right? 0 plus 2 times 1 half. If we consider these objects as vectors, in two-dimensional Cartesian space, then this product would correspond just to projection of one vector onto another, right? So as we do in geometry. But this definition can be upscaled to 3, 4, 5 even dimensional spaces. So one can define scalar product in anywhere. Now, so what if I swap the order and do CC times B prime? Am I going to get an error? Am I going to get single number, or it will be something different? So what are you getting? Just, huh? Just try it. So what it is? Yes. So if we swap the order of so if you multiply column by row, we still need to practice row by column. But now our row is very short, our column is not very tall. But we still practice row by column. So 0 times 1, row by column, 0 times 2, 1/2 times 1, or 1/2 times 2, right? So by swapping the order of this row and column, one is getting matrix. This operation has a tremendous meaning for our physical chemistry and quantum theory. So I'm going to I wouldn't tell that it is a secret, but it related to something that we did today in the class. So remember, if we have good functions, phi I, phi j, dx minus infinity to infinity equals either 0 or 1, right? So functions are vectors of infinite degrees of freedom, infinite dimensions. Product of functions integrated together is a scalar product, is like row by column. And if instead of multiplying them row by column, so it is number, and if you swap their order, then instead of number, they will generate operator. So swapping the order of a row and column in product of wave functions, one will get operator, density operator. Later on, we will get through it.